13.2 exponential growth functions. Essential question: how is the graph g of x equals ab to the x minus h plus k related to the graph of f of x equals b to the x power? We're going to start on page 713 in your book. We're going to look at two different graphs, one being 2 to the x power and the other being 10 to the x power. Now, on these exponential graphs, they're called exponential because they have a variable as the exponent. There's not a set parent function. So it kind of depends on what your bases are. And we're only going to look at two different bases, the 2 and the 10. So we're going to analyze base 2 and base 10 to the x power. So what we're going to do first is we're going to fill in the chart on page 713. All I'm doing is putting 2 to the x power in your calculator and getting points so that we can graph it and we can look at each of them individually. And then I'm going to put 10 to the x power in your calculator and we're going to get points and we're going to look at that graph. Now the way you do this, to that little caret or house top and then just put an x. So on the first table I have -3, which will give me 0.125. -2 is 0.25. -1 is 0.5. 0 is 1. 1 is 2. 2 is 4. And 3 is 8. Let's go ahead and graph that one. On the graph right here on the bottom of page 713, I would go over -3 and then up 0.125, which is right there close to the axis. -2, 0.25. I'm probably not close enough. -1, 0.5, which is a half. 0, 1. 2, 4. And 3, 8. So notice our graph gets really close to the axis but never touches, and then it goes up quickly, which is called an exponential. It's growing exponentially really fast. Okay, that's what an exponential graph looks like. So that right there is 2 to the x power. Okay, let's go back and let's put in 10 to the x power into our calculator. 10 to the x power, -3 is 0.001. -2 is 0.01. -1 is 0.1. 0 is 1. 1 is 10. 2 is 100. And 3 is 1,000. So let's graph 10 to the x power at the bottom of page 713 and see what that graph looks like. So if I plot -3, 1/1000, it'll be very, very close to the axis. -2, 0.01, really, really close to the x-axis. -1, 0.1, really, really close. 0, 1, 1, 10, 2, 100, which is way off of our graph. Look how quickly that one grew exponentially really, really fast, because 2 is all the way up to 100 and 3 is 1,000, so that's totally off the graph. Let's look at those two graphs and let's look at their domains and their ranges. I'm on page 714, letter C at the top. What is the domain of each function? So let's look at 2 to the x power. How far left, how far right does my graph go? Well, it goes continually, so I can put all real numbers. What about 10 to the x power? Left and right. Same thing, all real numbers. What about the range? The range over here, it does not go below the x-axis, but it does go above the x-axis, so y is greater than 0. What about the 10 to the x power? Same thing, it doesn't go below the x-axis, it gets really, really close, and then it goes up, y is greater than 0. What is the y-intercept on f of x equals 2 to the x power? Where does it cross the x-axis? I mean the y-axis right here. At 0, 1. Where does this one cross the y-axis? 0, 1. So what do you see about both of those graphs? Well, both of their domains are all reals. Both of their ranges are above 0. And they intersect the y-axis at 0, 1. They are getting increased. They are increasing drastically. And they are decreasing and getting very, very small. All right, predicting transformations of graphs. These are the same things we have done since day one. Let's look at, we're on page 715 at the top, part A. We have 1/4 to the 2x. We're going to fill these in kind of quickly. The graph of g of x equals 1/4 2 to the x will be the graph of f of x equals 2x vertical compression by a factor of 1/4. Second one, the graph of g2 of x equals 3 times 2 to the x power will be the graph of f of x equals 2x vertically stretched by a factor of 3. The graph on the next one, 2 times 10 to the x, will be the graph of p of x equals 10x vertically stretched by a factor of 2. And in the last one, the graph will have a vertical compression by a factor of 1/5. Moving on to part B. On the next one, the graph of g of x equals -3/4 2 to the x will reflect across the x-axis and have a vertical compression by a factor of 3/4. The graph of -5 times 2 to the x will be reflected across the x-axis and have a vertical stretch by a factor of 5. The graph -5/4 10 to the x will be a graph of p of x equals 10 to the x reflected across the x-axis and have a vertical stretch by a factor of 5/4. The graph q of x equals -1/4 10 to the x will be reflected across the x-axis and have a vertical compression by a factor of 1/4. Letter C, top of page 716. The graph of g of x equals 2 to the x plus 1 will be a graph of f of x equals 2 to the x translated 1 unit to the left. Same thing, remember it's opposite if it's with the x. The graph of g of x equals 2 to the x minus 4 will be translated 4 units to the right. The graph of q of x equals 10 to the x plus 2. We'll have a graph of p of x equals 10 to the x translated 2 units left. And the graph q of x equals 10 to the x minus 3 will be the graph of p of x equals 10 to the x translated 3 units to the right. Letter D, the graph of g of x equals 2 to the x plus 3 will be translated 3 units up. The graph of g of x equals 2x minus 5 halves will be translated 5 halves units down. The graph of 10 of x plus 5 will be the graph of p of x equals 10 to the x translated 5 units up. And the graph of 10 to the x minus 2 will be the graph of p of x equals 10 to the x translated 2 units down. Transformations are the same. It doesn't matter if it's quadratic, linear, cubic, square root, same thing. All right, let's go to your turn, number 7. We're going to graph g of x equals 4 times 2 to the x plus 2 minus 6. We're going to go ahead and put it in our t-table. That's, to me, the easiest way. I know that the x is going to be minus 2 units. I found that right here. Remember, it's opposite. Y is going to be 4y minus 6, just like before. Now, on these exponentials, you will have a horizontal asymptote. That means somewhere, either the x-axis or another horizontal line, our graph is not going to touch. That horizontal asymptote is going to be whatever the k is right there. K and y equals are the same thing. So k equals negative 6. So I know at negative 6, right here, I'm going to have a horizontal asymptote. Now, in order to have a t-chart, I've got to have 2 reference points. I'm going to use 0, 1, and I'm going to use 1, b. Now, b is going to be whatever that base is right there. In this case, it's going to be a 2. On some of your problems, it's going to be a 2. And on some of your problems, it's going to be a 10. But 0, 1, and 1, whatever the base is. So let's put those 2 points in there. If I put 0 in for x, I'm going to get negative 2. If I put 1 in for y, I'm going to get negative 2. 1 in for x, I will get negative 1. 2 in for y, I will get 2. Then we will plot those 2 points, negative 2, negative 2, negative 1, positive 2. So I know my graph is going to go through those 2 points, and it's going to get very, very close to my horizontal asymptote without touching it. There's the graph. What is my domain going to be? All real numbers. what will my range be? Y